Momentum is denoted by the letter P, and it is a physical creature that is equal to the mass times the velocity. Its direction is the velocity direction. It is common to use it to write the second law in this format. So, for what is it good for? It is another physical tool that helps us to solve physical problems. Let's see how. If there are no external forces acting on what we define as a system, then the momentum of the system is conserved. The momentum in the initial state is equal to the momentum in the final state. Let's say we took a few particles and defined them as our system. They can do whatever they want, for example, interact by colliding. As long as there is no force acting on the system, the momentum of the system is conserved. One example is if you let go to some box which is your system, its velocity will change because of the external force of gravity. Here is another example. The friction, which is the external force in this case, will cause the box to slow down, and so the momentum will change. Example. You are holding a bowling ball. You are m1 and the ball is m2. Suddenly, you give it velocity in a direction. And let's say you are on ice, so there is no friction whatsoever. We define you and the ball as the system. So let's say your mass is 80 kilograms, and the ball's mass is 4 kilograms, and at the beginning you are holding the ball, and everything is steady. When you throw the ball, what will happen to you? Will you move? By the law of conservation of momentum, we understand that yes, you will move, and we want to find your velocity. This I is an index that goes from 1 to 2, and V is used to initial velocity, and U is used for final velocity. We compare the momentum of the system in the beginning to the momentum of the system in the end. In the beginning, all velocities are 0, and by choosing the ball as moving in the positive direction, we see by this minus that you will move in the opposite direction with this speed. When the problem is in 2 dimensions, we use the law of conservation of momentum at each axis separately. A general format is as follows. Here, the black ball collides with the white ball, and then they both move. Let's define our velocity coordinate system, define the black and the white ball as our system, and let's assume that in the beginning the white ball doesn't move. So in x-axis, in the beginning, only the black ball contributes to the system's momentum. In the end, they both have some momentum component in the x-axis. So this momentum is equal to this momentum. Next, the same logic in the y-axis. Nobody moves in the y-axis in the beginning, and in the end, they both move where this is with a minus. Again, we compare the momentums, and we can isolate whatever the question wants from us. Talking about linear momentum, it is also important to talk about properties of collisions. We build a little table. We have 3 types of collisions. Elastic collision is where the momentum and the energy are conserved. Notice that each one of those is an equation where you compare between the initial momentum and energy to the final momentum and energy, and isolate whatever you need. On the other side, there is perfectly inelastic collision where the 2 objects that collide stick together and move together. The momentum is conserved and the energy is not. Check this out. And in between, there is a not perfectly inelastic collision where the coefficient of restitution is between the 2 edges 0 and 1. Notice that when you have a collision, the momentum is conserved in all cases. This gives you one equation enabling you to isolate some object. Then, if it is an elastic collision, you have another equation. And if it is a perfectly inelastic collision, you know that the velocities are the same at the end. Elastic collisions usually don't have modification of a shape and no heat. For example, 2 billiard balls colliding. An elastic collision usually have modification and heat. For example, throwing a ball at a pillow, the pillow will change its shape, there will be heat, and the ball and the pillow will move together.